That's all news to me, but okay, I'll strive to achieve this. Yeah. Okay, well, thanks for coming again. This is a continuation of what we were talking about yesterday. And today I'm going to focus on a few graph problems, and we'll try to see some reductions showing some equivalences and some hardness. Okay, so let me first start with the graph problems I'm going to consider in this talk. Here, for this talk, we'll just think of an undirected graph. It's going to have weights on the edges, and it will have n nodes and images. Okay, so the first problem I'm going to talk about is computing the eccentricities of the graph. So what is an eccentricity? For each node, its eccentricity is the maximum distance out of it. So you look at all the distances from x to all the other nodes, and you take the maximum. That's the eccentricity of x. Now, given that we know what eccentricities are, we can now define a few more parameters. One of them is the diameter. This is the maximum eccentricity, also known as the maximum distance in the graph. Okay. Then we also have the minimum eccentricity, which is the radius of the graph. So the center of a graph is a node that can reach all the nodes within the minimum distance. And this minimum distance for which a node can reach all the other nodes is called the radius of a graph. And it's the minimum eccentricity. Okay? Now, there's a different parameter that doesn't use the notion of eccentricity, but it's still very widely studied, is the median of a graph, which is just the minimum over all nodes x of the sum of the distances out of x. So instead of taking the maximum distance out of x, now we just sum all of them. So this is like finding a node that has the minimum average distance to everything else. Okay, so now we have these four things, and we can ask what is the fastest algorithm. And unfortunately, the best algorithms we have are we compute all the distances in the graph, and then you follow the definitions, and you get what the parameters are. So what this turns out to be, for dense graphs, we get roughly n cubed, and for sparse graphs, we get roughly n squared, where sparse here, I'll mean m is roughly n. M is order n, just here. Okay, so then the natural question is, why should we be spending so much time, especially for these three things here? We only really have to compute a single number. We're not computing n squared distances. We only care about one of them. Why should this take as much time as all pair shortest paths? And so we'll investigate this. Okay, and in general, can we suppose it's difficult maybe to get subcubic algorithms for all pair shortest paths, but maybe for these parameters we could do better. Maybe for dense graphs we can get n to the 3 minus epsilon, and maybe for sparse we can get n to the 2 minus epsilon. So, okay, and people have tried this for a long time, and we haven't succeeded. And then, okay, so let's do what we usually do. Let's relax the problem a little bit. And so then we can ask another question. What if we just want to approximate the answers? Can we do a little better? Okay, so this is the questions that I'm going to talk about. So in the rest of the talk, I'm going to just split the talk into two pieces. The first part, I'll talk about dense graphs, and the second part, I'll talk about sparse graphs. For whatever reason, the techniques that we use for dense graphs and sparse graphs are different. And one open question is to try to do something about that and bring these techniques together. We'll think about this later. Okay. All right, let's start with a dense graph case. So again, recall there we're computing all pair shortest paths. This is the best thing we know how to do. And we don't really know how to do it. It's substantially faster than n cubed time. And Ryan and I here, and then with Amir, Fabrizio, we show the following theorem, which is that if you care about beating cubic time by a polynomial factor, then all pair shortest paths is actually equivalent to radius, median, and many other problems. Okay, so we've shown that in the dense case, two of the parameters we discussed are actually equivalent to all pair shortest paths in the sense that if you had an n to the 3 minus epsilon algorithm for one of the problems, then the other problems also have an n to the 3 minus delta time algorithm. All right, so I will recap what I said yesterday, but in the context of cubic reductions, subcubic reductions, and I changed the picture a little bit to make things a little bit more clear. So a subcubic reduction from problem A to problem B is an algorithm. This is the algorithm, this arrow. It takes an instance of problem A, then it runs some algorithm that produces instances of problem B, and these instances, they may be produced adaptively depending on the answers. So these instances you feed to some algorithm, and depending on what the algorithm says, you may change what the next instance will look like. But no matter what this algorithm does, no matter what sequence of these instances you produce, you guarantee that when you take their sizes to be n1, n2, and so on, the sum of the n sub i's to the 3 minus epsilon is less than n to the 3 minus delta. So when you do this, what do you get? You get that if you have an n to the 3 minus epsilon algorithm for B, then you get an n to the 3 minus delta algorithm for A by running the reduction and summing up the runtimes for the B's, which exactly follows this. So, okay, so this is the type of reduction we're going to show. And in fact, I will give you an example where we actually produce a lot of instances of B adaptively. So this is not always the case. Often we actually only produce one instance, but for the example I'm going to show you, actually need to do this. Okay, good. So pair shortest paths is equivalent to radius and median for the purposes of this talk, and also eccentricities. Okay, so let me flash this slide again, just in case you weren't aware of the long research of all pair shortest paths. It has been a notoriously difficult problem to improve on n cubed. Small improvements have been possible, but they have been really, really hard to obtain, and new techniques have been developed with all of these papers. And in the end, Ryan even through complexity of the problem, and still you only get something that's less than polynomial. It beats all polylogs, though, so it's a huge step towards what we want, but we're still stuck. So, and this essentially shows that if we did the same on these parameters, we have this same problem. And it's a little discouraging, but maybe it's not that discouraging, because now we can just attack these simpler looking problems, and maybe they have more structure. Okay. So there's this conjecture that I mentioned yesterday, which says that let's take the word RAM model with order log n bit words, and there all pair shortest paths is conjectured to take n to the 3 minus little o of one time. Okay. So here's a few more problems we've shown to be equivalent to all pair shortest paths. Here's all pair shortest paths. There's something called the distance product that I will define. It has been known for a long time that these problems are actually equivalent. They have exactly the same complexity within constant factors. And all of these arrows here, they signify reductions from the problem to a problem, and they were all known. Just because all of these problems, they're just special cases of all pair shortest paths, so you can just use an algorithm to solve them. So median we define. The Wiener index is just the sum of all of the distances in a graph. Now betweenness centrality is something about how central a vertex is. So it says roughly how many shortest paths go through this vertex. Actually, it's the fraction, and you have to reweight it a little bit, but it's a very important problem in social network analysis. So it turns out that We can put it on the board here. Replacement path, here you're given the shortest path between two vertices, S and T, and you want to know for every edge on this shortest path, what would the new shortest path between S and T be if I were to remove this edge? And this problem is not too hard to reduce to all pair shortest paths, but it also turns out to be equivalent, as we'll see. Okay. Second shortest path is an even simpler problem, which is, I mentioned it yesterday. Instead of computing the shortest path between two nodes, we now want to know what's the second shortest path on the list of shortest paths by distance. Radius we defined. Distance product verification. Distance product is some sort of matrix product that I'll define. Distance product verification just asks, given two matrices, and a third one, tell me if the distance product of the first two equals the third one. And so on. So these are the problems here. So how did we show equivalences? Well, we showed a reduction in the opposite direction between this problem, which I haven't defined yet, and distance product. So this problem is actually a very, very simple problem. You're given a graph, and it has edge weights. And you want to find three vertices that are all connected to each other, so a triangle, and the sum of the edge weights has to be negative. And it's a decision problem, does such an object exist or not? And it turns out that under subcubic reductions, distance product is equivalent to negative triangle. And because negative triangle is so simple, you get all these other arrows, and then you can complete the picture. And now you can see this is a strongly connected graph. And, okay. So this is what we're going to try to show. I'm just going to show you two arrows in this picture. I'll show you this one, and I will show you, I'll mention what this is. I think it's pretty nice to see. And I'll show you the one to radius. Any questions up to this point? Yes?
Equivalence here, that means they can reduce to each other according to the fine grained reduction?
Yes, we did this fine grade reduction. I showed it on the previous slide, and you'll see examples of it. So, and they're equivalent in the sense that if you get an n to the 2.9 algorithm for one of them, maybe you get an n to the 2.999 for the others. But you preserve subcubicity, so in this case. Okay, I'll start with defining distance product and giving you some idea of why it's equivalent to all pair shortest paths. The distance product is as follows. You're given two matrices A and B, and you can think about the usual matrix product, except that now I've replaced the sum with a min and the product with a plus. So it's the min over k of aik plus bkj. Okay? It's also called min plus product. All right, so if you had a T of n time algorithm for all pair shortest paths, then you can also solve the product in the same time, and this is not too hard to do. The way you do it is, let's say I'm given two matrices A and B. I can just build a graph out of them in the following way. It's going to be tripartite, and I'll just put them as layers, left, middle, and right. And I'll put edges from the left to the middle with where the weight, and I'll put a weight of the edge, which correspond to the entry in matrix A. There will be no edge whenever it's infinity. Okay. Now, for the edges between the middle and the right, I put the weight of them corresponding to matrix B. So in the on the edge from K to J, I'll have the KJ entry of B, and on the edge from I to K here, I'll have the IK entry of A. And now this graph is directed from left to right, and if I compute the shortest path between every node here and every node here, I will actually get exactly the entry of the min plus product to the distance product. Because for this graph, the distances are just the minimum weights of paths of length 2 from left to right, and then this is exactly the distance product. So you can also go in the other direction in the following way. Okay, so what do? You make some observations. The first thing is I'm just going to take my graph and I'll create a matrix out of it as usual. And the way you do it, you put an infinity when there's no edge between UV. You put 0 when U equals V, and the weight of the edge otherwise. And now we do successive squaring. Okay, and you notice that if we compute the kth power of this matrix under the distance product, you will get the weight of the shortest path that has at most k edges. So when you do 2, when you multiply it once, you'll get two edges just on the previous slide, and so on. And you can compute a to the k with successive squaring with log k products. Now, you know that all the shortest paths are without loss of generality simple, and so they have length at most n minus 1. So you only have to repeat this log n times to get all the distances. And this will give you that all pair shortest paths only has to do roughly log n queries to this distance product. Turns out you can get rid of the log, so these problems are actually equivalent. This was proven, for example, by Fisher and Meyer in 71. All right, so now you know what distance product is, and now we can forget about paths and graphs and just focus on distances, on distance product. All right, so we're back to this picture. I have shown you this arrow, and now I will use my pointer. Okay, now we'll do negative triangle or distance product. We'll show the meat of the reduction. Okay, again, this was in 2010, a long time ago. All right, so let me remind you what negative triangle is. You have a graph. It has some edge weights on its edges. We can even assume they're integers. And we'll, given this graph, we want to say whether there are ijk such that when you take the sum of their edge weights, you get a negative number. You want to say no otherwise. So there's a trivial cubic time algorithm. You try all triples of nodes and you check the condition. And we don't know how to do better. Again, just as usual, I am fascinated by problems where this happens, so you can just assume this happens for every problem I say. Okay, so we will reduce distance product to this simple looking problem, and we'll do this in 2 steps. The first step is to take an intermediate problem. We'll call it all pairs negative triangles, and in this problem, we want to know for every pair of nodes I and j, are they in some negative triangle? So is there k such that the sum of the weight of ik, so wkj and wji is actually negative? So I wrote it in this funny way for a reason, and you'll see in a little bit, but it's the same thing. That's what it is. Okay, so the first thing we'll do, we'll reduce distance product to this intermediate problem, and then we'll convert the intermediate problem, a problem where you need to compute something for all pairs of nodes, into something that only needs to decide a single condition. Okay, so I will start with the first part, and then I'll show you the second part, which will be the second part will be the most interesting part of the reduction. Okay, so let's take a distance product instance, and just as I showed you in the reduction to distance product, I can convert it into a graph problem. So given 2 matrices A and B, I convert it into a tripartite graph with partitions I, K, and J. The edges from I to K correspond to entries of A, and the edges from K to J correspond to entries in B. But B and A are the same here, so okay. So we know this already, so now I'm going to do something funny. So suppose I start putting edges between J and I carefully pick some edge weights to put on them. So I start with this graph, and I start adding new edges. And now what do these new edges tell us? Okay. If we take this graph and we put the new edges and feed it to an algorithm that solves all pairs negative triangles, in particular, it will tell me for every pair of nodes I and j in these two partitions, is there some k in here such that I, j, and k form a negative triangle? And so when we look at this is actually an A, but okay. So then you get, is there a k such that aik plus bkj is less than the weight or less than the negative of the weight that I stuck in here? But okay, so if there is such a k, then actually it's equivalent to asking whether the minimum of aik and plus bk and j is less than this. Because if we have some k for which it holds, then in particular for the one that achieves the minimum, it has to hold. Okay, so what are we saying? We're saying that I can put a bunch of numbers here, and I can check in parallel with a single call to all pairs negative triangles whether my guesses for the distance product entry ij is too big or just right or too small. So this tells me I can do a binary search, and I can simultaneously do a binary search for all entries I and j. And I do this, like after each call, I change my numbers that I put here depending on what the all pairs negative triangle instance told me about I and j. And this is where I needed it to tell me about all the pairs, because I want to be able to search. All right, so I do a simultaneous binary search, and then I get my reduction. Now, there's something I'm sweeping under the rug. The binary search will have a logarithmic dependence on the weights. Okay, so maybe I'm cheating, but it turns out that with some more work, you can get rid of that, and you can replace it with a log n factor. So, yeah.
What do you assume about the output of the all pairs negative triangles? For each ij pair, it tells you whether it's...
It tells me a bit. For each ij pair, it tells me is there a negative triangle between I and j, including ij or not. So it gives me a Boolean matrix. So that's the output.
So maybe I missed something at the beginning. Do you generally assume unit cost arithmetics?
Sorry?
Do you assume unit cost arithmetics?
It's in the word RAM model, but we don't even need that. Just if the edge weights are of size up to m, they're integers, then I pay log m to do the stuff, but then I can get rid of it. Okay, and you can assume if you're worried about the cost to actually do the computations, assume that the integers fit in the words, and then you're okay. Okay, this step clear? Good. So we have this step now, and we've reduced distance product to some problem about triangles, but we have not gotten rid of the part where we need to do things about all pairs. And this was where we were heading. So this is where this step comes in. So now we take this all pairs negative triangle instance and convert it into just decision question, is there any negative triangle in the graph? And I'll start with the idea, and then I'll show you the full proof. So the idea is sort of, I assume that my graph is tripartite, which you can assume without loss of generality. So now I have these partitions I, j, and k. And what I'm going to do is, for each of the partitions, I'll just split them up arbitrarily into pieces of roughly the same size, and I'll pick the parameter s, which will tell me what the size is. So I take j and I split it into pieces of size s. There will be n over s pieces here, the same with k and the same with I. And then the first attempt is I'm going to take every triple of pieces. I'll look at the induced subgraph, and I'll make a call to negative triangle there, and now we'll learn whether this triple of pieces contains a negative triangle, and if it does, then I can set this entry in my output of all pairs negative triangles to 1. Okay, we're not avoiding anything yet because we still have to do all triples, and it might take us too long. But the point is that if you did that, then your call to negative triangle is only on pieces of size S instead of N. So it seems like we can do something with this. All right, so now that you know that we've partitioned the graph into pieces and we're doing stuff on triples of pieces, I'm going to give you the full reduction. So the reduction is as follows. Let's say C is going to be my output. Originally it's all zeros, and we'll fill it up with ones whenever we learn that ij is in some negative triangle. We'll put a 1 there. Okay? Then we start iterating the following process. We take every triple of pieces in turn, and we look in the induced subgraph. Let's say first we take I1, J1, and K1, take the union of these nodes, look at this induced subgraph, and then we check whether this subgraph contains a negative triangle. And while it still has one, we actually find it. Okay, finding actually you can do with the detection algorithm is with self-reducibility. It's not too hard to show. So you find some negative triangles. So this will be some AX and AY and piece I and J, and then with some K over here. And then we just record in the output matrix that we found a negative triangle there. Okay, so far is what I said on the previous slide. Now, the next thing we do is actually we change the weight of this edge that we just discovered is in a negative triangle. We make it into an infinity. And that concludes the algorithm. Because, well, the moment we learn that this edge is in a negative triangle, we can just remove it. This is what effectively we do. When we set it to infinity, this edge will no longer be reported, ever, through the algorithm. So when we remove it from the entire graph. So in particular from all the pieces that we call the algorithm on. And so the number of times we ever return a negative triangle is at most n squared. This is the algorithm, the reduction. I will analyze it on the next slide. So, all right. What's the runtime? Okay, first of all, the correctness should be clear. We're actually kind of searching through everything, and the moment we find something, we record it, and we just saved a little bit of work by not reporting things more than once. So the runtime is the number of triangles found times the time to find a negative triangle, which is this, plus the number of triples times the time to assert that the triple no longer has a negative triangle. Okay, so this is the runtime, number of triples plus the number of triangles found times the time to run the negative triangle algorithm. Now, the number of triples we carefully picked to be n over s cubed, where s was the size of each piece. And the number of triangles we found, we guaranteed that it's no more than n squared, because we guarantee that no edge will be checked more than once. So, okay. And it only costs the time to do a negative triangle call on graphs of size s instead of n. Now, what we usually do is we sort of balance things out. Let's assume that the time to find a negative triangle is n to the d, for some d hopefully less than 3. And then we balance things so that s is n to the 1/3. This makes this be the same as n squared. And when we do this, we get that if we had a negative triangle time algorithm that runs in n to the d, then we get an n to the 2 plus d over 3 time algorithm for all pairs negative triangles. Now, it's not the same runtime, okay? But I didn't say I would give you that. I said that whenever this is subcubic, this one will be subcubic. and this is true. Okay, so this is an example of an adaptive reduction that's fine-grained, and if you notice, it fulfills all the definition that I showed you, and it gets something completely non-trivial. So, and we have similar reductions for other problems, but this is sort of okay. Yeah.
Is the reason why you don't set C of AX a C and C of AY a C and so on?
Well, the question is, why didn't I set these two edges in the output to be? This is because I defined the all pairs negative triangle and that I only care about the pairs between partitions I and J. That's why. But yeah, you could also solve the other problem. You can just change the change the names of I and J in case. All right.
Maybe I don't understand. So don't you have sometimes run the same triple many times, because maybe that same triple is leading to many edges, right? Like when you set that edge, which you discover, you set it to infinite, but maybe there is another edge in that triple.
Well, this is a tripartite graph, so the only triangles go like this. The moment I set this to infinity, it cannot appear in any more negative triangles.
But your oracle is only giving you that one edge, right? Maybe there is another edge in that triple, like from...
Oh, it could be. That's why I keep doing it. While there's a negative triangle, I check it again. Oh. Is there one? I do it again until I've exhausted all the negative triangles in the triple. So, yes. So you don't only find a single negative triangle in the triple, you just keep doing it. And this is why we had to split the runtime into this. But, all right, so what we have shown is the central part right here that sort of makes everything work. And I'll show you a reduction now from the simple problem to radius, and we'll see how these things typically go. Okay, this was in 2014, a year ago, I guess. Okay, so now we'll make some changes to the negative triangle problem, which are true without loss of generality. The first thing is, as we've been doing so far, we can assume the graph is tripartite, just because we can just triple all the nodes and put a copy of each edge, and the number of triangles is preserved in a constant factor, and everything still works out. Okay, so we can assume this graph is tripartite, and we're just looking for a negative triangle, and it will have a node in each of the partitions. And the second thing we can assume is that it's a complete tripartite graph, just because if the maximum edge weight was m, we can just put edges that have weight m to represent the non-edges, and we don't even have any infinity weights that way. Everything has weights between minus m and m, and it's a complete tripartite graph. Everything is fine. Okay? This helps us with reductions. Doesn't makes things easier. Okay. So I added this non-edge, and I put 9 because 9 is the largest edge weight. All right, so now I'll do another modification. In a negative triangle problem, we were asking if there's a triangle of negative sum. Now I'll just add some quantity to all the edges, in particular the largest edge weight plus W, where W is something that's bigger than M. And for some reason it's not showing, but okay. This faux is supposed to be W greater than M. Okay? Imagine it. All right. So now what we'll do, after we've done this, what we have is that instead of looking for a triangle of weight less than 0, we're looking for a triangle of weight 3 times this quantity, because you have 3 edges in a triangle, and each edge got an extra M plus W on it. Okay, so we didn't change the problem too much. We just reweighted it a little bit. And this also makes all the edge weights non-negative, and yeah. Okay, So now what we'll do is we're going to take the triangle, negative triangle instance, and we'll create a graph out of it that will have 4 layers. So the original graph had partitions A, B, and C, and now we have a layer that has a copy of all the nodes of A. Then we have a layer with a copy of all the nodes of B, a copy of all the nodes of C, and a second copy of all the nodes of A. So we have B and C appearing here, but A got split into 2 pieces. And okay, now what we'll do is just what you suspect. We'll put the weights, the weight between A and B, between the pairs of A and B, the first copy. We put all the weights just as they were in the original graph between the respective copies. All right, so now what we'll get is that so for any A and its copy, A prime, and this side, we'll have a path of length. The shortest path will be the length of the minimum triangle between that contains A, okay? And if the minimum triangle was less than 3m plus 3w, then the distance between A and A prime will be less than 3m plus 3w. We don't have a very nice guarantee about A and anything else. So we'll add some edges, and we'll add an edge between A and a node that's different from its copy, so any other node. And its weight will be 3m plus 2w, so it will actually be less than 3m plus 3w. And what we've achieved now is that for any node A, its distances to the right part are less than this quantity, 3m plus 3w, if and only if it's contained in a negative triangle, in a triangle of weight less than 3m plus 3w. So that's what we achieved. And we're trying to get something about the radius, and in order to do that, we'll force the node whose eccentricity is the radius to be on this side. And when we do this, then we'll ensure that the radius is less than this quantity if and only if this node has a negative triangle in the original graph. Okay, to do this, we add this bizarre thing here. We add 2 nodes Z and W that are roughly the same in the sense that basically these nodes here have edge weights of the same number, m plus w to x and y, and some other number to w and z. And these numbers were chosen so that first, every pair of nodes here are close. They're at distance 2m plus 2w. And every node, except for the nodes in A, is very far away from z and w. So this is how we chose them. So every node, except for the nodes in A, is far away from z and w, in particular distance bigger than 3m plus 3w. But the nodes in A are a distance less than 3m plus 3w. So now what we get is that the center node must be in here, and the radius is less than 3m plus 3w if and only if there is a negative triangle in the original graph.
Why would we need 4 nodes, not just one with like all the edges to the...
Are you asking why we need these? Well, okay, just think about, if we only had one, then this node can be the center. We want to avoid this. So when I put this node here, I made these all be close, and I put this node can now be the center, so I make it not be the center because it's far away from that one. So it's a little tricky, but you have to do this. Yeah.
What about paths that go like from A to E by the red edge, and then like E up to C, and then C to A? Can you get?
Yes. Yeah. Okay, so there's another technical thing. Thanks. So you have to be careful because there's all these paths here that go like this. So you have to make sure that they're not too short. And this is why we have to pick W to be large enough. Okay, because and we know that all the edges are that are bigger than W. Okay, so in particular, this path, the way we've chosen, if it goes back and forth, it gets 2w onto the 3m plus 4w, and now it becomes bigger than what we want. So you have to make sure that all the pairs are satisfied, but if you pick the weights in this way, it works. Okay. So this shows that if you have a really, really good algorithm for radius, it gives you a good algorithm for negative triangle and a good algorithm for all pairs shortest paths. Here we didn't have to do anything fine-grained. We actually just got an instance of roughly the same size. So this is sort of what you typically expect. But we did have the fine-grained part from all pairs shortest paths to negative triangle. Okay. Questions? So that's what I said, every node, blah, blah, blah. And I put this stuff to tell you that the distances to all the other partitions are small, but it's not that important. You just pick the weights for it to work out. Okay, so what we've done so far is we've covered everything I was going to cover about dense graphs. We did this part, and the yellow direction we knew. So this cycle is now complete. And all the other reductions have some sort of similar flavor. You have to carefully construct the graphs. It doesn't always work. We thought that it will make it work for diameter, but things just don't work out. Okay. That was the end of dense graphs. If you don't, do you have any questions on dense graphs? Otherwise, I'll move on to the sparse graphs since I'm a little bit slow today. All right. So for dense graphs, we had these nice equivalences. For sparse graphs, we don't have that yet. So what we get for sparse graphs, we get some sort of hardness based on some conjectures, just like I mentioned yesterday. And here's something we can get. Well, okay, this is just repeating what I had before. Here we're fighting against n squared. All the parameters I mentioned you can solve in n squared time by just reducing them to all pair shortest paths. And even when we have unweighted graphs. See, for the dense case, the problem is hard mainly because they're weights. When the graphs are unweighted, we can solve them in subcubic time. But in sparse graphs, the weights don't play much of a difference. It turns out that we're even stuck on unweighted graphs. So, right. And again, for all pair shortest paths, even if we solve it in optimal time for sparse graphs, we would still be paying n squared. And here it's unclear why these problems should require n squared because they're just single integers. So, and then again, what about approximation algorithms? Maybe when you approximate things you can do it in linear time. And here's something we're able to show. We were able to show that you can actually get some constant factor approximations in subquadratic time. For example, for diameter in sparse graphs, you can get a 3/2 approximation in, let's say, n to the 1.5 time. Or it's the same thing for radius, and for all the eccentricities, you can get 5/3 approximation, again in n to the 1.5. The median problem is easier, much easier when you allow for approximations. You can get an approximation scheme that runs in roughly linear time. So somehow when you have sums, it's much easier to approximate than when you have minimum. So, okay. So this is all that's known for approximation algorithms, as far as I know. And we actually show that all these ratios, 3/2, 3/2, and 5/3, are tight for subquadratic algorithms under some conjectures. So for me, the most surprising was this 5/3. I don't. Anyway, okay, because we thought that the minimum and the maximum eccentricities can be approximated within a factor of 3/2. Why can't we approximate all of them within a factor of 3/2? But it turns out if you want all of them, somehow 5/3 is the right answer. So, okay. So here's the sparse graph conjectures that we use. The first one is the orthogonal vectors conjecture I mentioned yesterday, which is given two sets of n vectors each with some maybe slightly super logarithmic dimension, are there two vectors that are orthogonal? And the conjecture was that if you want to solve this problem on the word RAM, let's say, it requires n to the 2 minus little of 1 time. And I have showed you the proof of this theorem that strong ETH implies the orthogonal vectors conjecture. So if you believe strong ETH, you need to believe this one too. And then there's a slightly weaker conjecture. So this is this other problem that I haven't defined yesterday. This is different. So here you're given two sets, U and V, of subsets of some universe K, of the integers 1 to K, where K is something slightly super logarithmic. And you want to know, is there some set here that hits all of the sets here? So by hit, I mean it contains some element of each of the sets. So it's the hitting set problem. And the hitting set conjecture is that this problem also requires n to the 2 minus little of 1 time. It has been studied within the context of data structures in one way or another. And we thought it's actually, we can prove that it's actually strictly, well, it's not strictly, it's easier than orthogonal vectors. So if you believe the hitting set conjecture, then you should believe the orthogonal vectors conjecture. You can reduce hitting set to orthogonal vectors. So, okay, so we have these are the two conjectures that we use in sparse problems. And
Excuse me, Virgil.
yeah.
Why did you call it like that, hitting set, and not, I don't know, non-orthogonal vectors? It seems to be...
Oh, but it's not non-orthogonal vectors. For if you translate it into vectors, it would be there exists a vector in one set that is not orthogonal to any of the others. I don't know. It's kind of makes sense.
Hitting set is the right name because a hitting set is a set that intersects all other sets.
Exactly.
No,
So it's asking, is there a hitting
that's
set
correct.
in U?
What I mean is that I like the fact that so you can phrase it as vectors.
You can phrase it as vectors.
I like the fact that
We can also phrase this as subsets. I mean, we can go back and forth. You're right. There is some type mismatch, but I like the name is the right one. So. Okay, so we have these two conjectures. One is more believable than the other, but we can prove the following. This is a picture of some of the things we know, at least with respect to the parameters I define. You can reduce orthogonal vectors to beating 3/2 approximation in subquadratic time for the diameter and for 5/3 for the eccentricities. You can reduce hitting set to the median and approximating the radius. So this is what we know. And I think in the amount of time I have, I will just show you this one, which is relatively simple. Okay. So potentially radius and median are easier. That's what you should get out of this. Okay. So here's what we'll do. We'll take the problem of distinguishing whether the diameter of a graph is 2 or 3. And we'll reduce orthogonal vectors to this problem. And this will mean that if we get a better than 3/2 approximation algorithm for diameter, in particular, we can distinguish between the diameter being 2 and 3. And therefore, we can also solve orthogonal vectors and CNF set, K-sat for OK. OK. So the reduction is very, very simple, pretty fast to do. So what you do is you take the orthogonal vectors instance, and we'll create a tripartite graph out of it. On the left side, we'll put a node for each vector. And on the right side, we'll put another node for each vector. And then in the middle, we'll put a node for each coordinate of a vector. We'll put the 2 extra nodes x and y just to help us with distances. Then what we'll do, we'll put edges from y to everything on the right, edges from x to everything on the left. And this guarantees that the distance between any node on the left and any node on the right is at most 3. Okay? And also guarantees that any nodes on the same side are distance 2. Now, we'll also put these edges from x and y to everything in the middle. And this also guarantees that any coordinate is a distance 2 from any other coordinate and everyone else. So if the diameter is 3, it better come from 2 nodes, one on the left and one on the right, because it cannot come from any other pair. So now we will put edges between vectors and coordinates in the following way. For any vector v and any coordinate c, we will put an edge if and only if that vector is 1 in that coordinate. The same thing here. We'll put we'll put an edge between d and u if u is 1 in coordinate d. Okay. And this completes the reduction. And what do we know? First of all, we know that every pair of nodes that is not one on the left and one on the right are at distance 2. And now we get that for every pair of nodes, v and u on different sides, they're distance 2 if and only if they have a coordinate in which they're both 1. And if there's no such coordinate, their distance is exactly 3 by going through this x and y. So this means that the diameter is 3 if and only if there is an orthogonal pair, and it's 2 otherwise. So distinguishing between 3 and 2 tells you if there's an orthogonal pair, and yeah. Yes?
Just curious, what if we had the orthogonal vector problem where the entries are integers rather than just 0 or 1?
Okay, so he's asking what happens to orthogonal vectors if the entries are integers. So if you work over the integers, we think it's a strictly harder problem. If you work over a finite field, there's actually faster algorithms. Right, so this is a very simple reduction. And the way you do the radius reduction is you take the hidden set problem and translate it in a very similar way. And I think I don't have time, right, Thor? Good. Okay, so I'll skip that one. There's the reduction. I'll put the slide somewhere. There. So a few words about radius and diameter. The funny thing is that every algorithm we've had that works for radius also works for diameter and vice versa. So it's kind of annoying. You can't prove that they're equivalent. The only place where they differ is in the quantifiers. So one problem is about max-max, the other one is about min-max. And that actually makes them quite different when we try to prove reductions. We actually think diameter is possibly easier than all pair shortest paths in dense graphs, or it might just be hard to improve on n-cubed for some completely different reason. We actually have some equivalence class around diameter in dense graphs. For example, if you want to approximate the betweenness centrality of a vertex, that's equivalent to the diameter problem. Okay, so here's some open questions, and I'll conclude with this. Can we get any hardness for the diameter problem for dense graphs? Maybe you assume some other conjecture that's not all pair shortest paths requiring n-cubed time, maybe something else. Can we explain why we're stuck? We don't have anything yet. Can we find some other equivalent graph problems? So far, we've mostly been working with shortest paths related problems. Maybe we can think about other things. Can we relate the sparse and dense case? There's something, I don't know what to say about the middle. Can we prove something like this? Does an n to the 1.9 algorithm for sparse diameter imply n to the 2.9 for dense diameter? No idea. Maybe not. Maybe yes. I don't know. Okay. So can we show any approximation hardness for any problem in dense graphs? Not for all pair shortest paths, because we know we can approximate it with Uri's algorithm in n to the omega time. But maybe some other problems we can show some approximation preserving reductions, and we haven't been able to do that for dense graphs. And what about the actual runtimes we get for 3/2 approximations? When we have a sparse graph, usually we get n to the 1.5, and why can't we do linear time? So we don't have a good answer for this. And so this concludes my talk, and thank you.
Thank you very much, Virginia. questions?
Is it possible that with this free, because you have ruled out like distinguishing between 3 and 2, this is exactly the same situation I've seen in packing. It doesn't rule out to have some asymptotic pitas or something like this one, like that word gets better approximation if it's unweighted and the distance is like 1000 and 1010 or something. I mean, like approximation in the form like, I don't know, 1.2 times opt plus 10 or something.
Okay, so he's asking, do we only get 2 and some hardness about distinguishing 2 and 3? Can't we just get some very nice additive approximations, right? No, we cannot get additive approximations for the same reason. We have reductions showing that no constant, no constant additive approximations are possible. Again, assuming orthogonal vectors, you can prove, that mixed approximations are not possible in some settings, and yeah.
In the Sparse case, couldn't you just put intermediate vertices along every edge to stretch it out?
This will show you between 2D and 3D, but it's not sufficient. Well, maybe there's something going on when you try to prove additive approximations. You have to do more work. So that's all I have to say.
So the orthogonal vector conjecture is it's very believable because it's applied by EH, right? But can you motivate a bit better the eating set conjecture? Because that's kind of...
Okay. So the hitting set conjecture is just, you just modify the orthogonal vectors conjecture in a sense to change the quantifier so the reductions work in a sense. But we also try to solve it because we really believe it's simpler, right? It's a simpler problem, but none of the techniques seem to work. Okay, so maybe, so the reason why we consider these reductions is because maybe we can solve this problem and get some intuition about what to do with when the quantifiers are different. And actually, this it's a good question. It comes up in other problems that people have studied a lot. So there's these problems in graphs that are similar to finding a triangle. So, for example, there's a problem called simplicial vertex. Here you're given, you want to find a node such that its neighborhood is a clique. Okay, so this is again, it's a similar quantifier swap there, and it's believed to be easier than triangle, but it has been studied for many, many years by a lot of researchers, and the best algorithm is 2n to the omega. And anyway, so there's a lot of different cases where this sort of quantifier swap happens, yet we still don't have a better algorithm. And this was studying this problem is something that will allow us to learn something more.
One general question, what properties of the graphs, like bounded degree and so on, from your reductions might be influencing whether it would be hard or not?
Good question. So the question is, what properties of the graph in the reduction make the problems easy or hard? So one thing we noticed is that if you look at the reduction, the graph has kind of small tree width, if you saw yesterday's lecture. So the tree width is log n, order log n. So then this will give you some hardness for graphs for getting algorithms in terms of tree width, and in particular, it led us to ask the question: what if you wanted an FPT algorithm that runs in linear time and has some running time that's small in terms of the tree width, or other parameters that follow from this reduction? And we were able, this reduction already shows a 2 to the whatever, tree width lower bound, to the little of tree width times n lower bound, or n to the 2 minus epsilon even. But you can also show an upper bound that's close to that. And then you can do a lot of stuff like this and actually still open what other parameters one can explore.
Okay, I suggest we thank the speaker again.